This problem asks us, so we have a synchronous generator, it's 9.7. With the following parameters. So RS is equal to 0, no synchronous resistance or resistance on the field windings. The synchronous, armature windings. The synchronous reactance is 1.2 per unit. The terminal voltage is 1.0 with an angle of 0 per unit, and it's supplying 1 per unit power. So the P out is equal to 1 per unit. And so what it asks us is to draw a phasor diagram for all relevant quantities. Based on 3 different cases. Consuming 0.5, all of them per unit. So if we go back and look at the circuit that's relevant for this, we're talking about this one right here. So VT, I was writing a lot of stuff down, you couldn't see it. Anyway, so the circuit that's relevant is this one here. And so all it's really asking us to do is to draw the phasor diagrams that are associated with that. So, and I'm going to bring up MATLAB on the computer here so I can just do some of the calculations without doing it by hand. So, and this is a good review because, as you all know, you have the quiz on Thursday, and a lot of those potential problems would encompass something similar to this, having to work with these vectors and all that. Okay, so first things first, we know we always start off when we draw these diagrams, well, 99% of the time, we start off by drawing VA because it's normally considered to be the reference. So what I'm going to do is try to do a makeshift. So 1, 2, 3, 4. So we'll call this each mark will be a half per unit. So we'll say that this is our VA. So VA, okay, has an angle of 0 degrees. The next vector we're normally going to draw is going to be our IA. And so how do we progress with that? So we know that okay, so this is case number B right here. Okay, so the next thing we need to draw is we need to draw IA. How are we going to figure out what IA is? Well, let's write down the values that we know. So what are some potential equations we could use to get IA? We know that SA would equal VA times IA conjugate. And actually that should be good, right? Good enough for us because we know both those values. So what we can say is that IA will be equal to the conjugate of SA over VA. And so what's the value for that? That'll be 1 plus J 0.5, right, because it's supplying Q 0.5 over 1. And so what's the value we get for that? Well, it's itself, right? It's divided by 1. Sorry about that. Let me just go ahead and get it in the polar form, though.
Isn't the conjugate?
Oh, I forgot to take the conjugate. Yeah. But still, I'm going to get it in polar form. Absolute of 1 minus J times 0.5. And then angle. Yeah. That's a good question. I mean, all this you can do on the calculator. It's only like, it'll take maybe a minute or 90 seconds as opposed to taking like 10 or 20 seconds. But that being said, I mean, yeah, I guess I really don't have an issue with anything. I mean, I would like, since this is an in-class exam, I mean, no Googling or anything like that, but we'll just go on the honor method. But yeah, sure, if you want to use MATLAB. But you be careful with MATLAB, though, because you should still show the steps, right? When you're doing it take home, you can sort of like do screenshots and include that as part of your solution, but you know, you won't have that opportunity for doing it in class. Okay, so the angle, so it's 1.1180 with an angle of negative 26.5 degrees or 6 degrees, give or take. Okay, so now if we draw our IA, it'll approximately look like this, and the angle in here will be, we'll go ahead and call this the theta A. That'll be theta A in there. Okay, now we know that if we were to assume this to be straight, going straight up, right, the angle difference here is the same as the angle difference between the blue and the green, right? But the length we don't know yet. This is going to be our XS IA. So the length is really what we need to know. It's going to be 1.2 times the 1.2 times 1.1180. So the length is 1.34. I'll go ahead and write that down here. So XSIA will be equal to 1.3416, and the angle will be 90 minus, I'll just go ahead and multiply them together. J times 1.2 times 1 minus J 0.5. I'll show you what I'm doing in a second. Okay, so if you look what I did on the computer here, just to verify that everything is as we would expect. So I calculate this value I call KO1, which is XS times IA, and that's equal to J times 1.2, this is our XS value, times the IA value. Okay, the magnitude comes out as we would expect if I just took the current and multiplied by 1.2. The angle is where we just want to check. So the angle is 63.435, but if you look at the way that it's drawn in the figure, we said that those two theta A's are equal to each other, right? But this angle here is really the one that we're calculating. So in order for to get a match, we need to look at 90 minus whatever that angle is. So that should also be equal to 26. Which if you look here, it is. So 26, 26. Okay? And the reason why one's negative and one's positive is because I guess I should have reversed it and done the factor minus. But anyway, the difference is the same. And then lastly, all we have to do is get the last vector, which is going to go from the origin all the way out to here. And that's going to be our value of EAF.
The excess IA calculation, do we take into fact the degree of excess or just the whole value?
No, you have. Yeah, you have to. If you go back and look here, when I did the calculation, well, so there's two ways of doing it.
Mm-hmm.
When you're drawing it, you can assume you already know the angle, right? Because you're just taking 90, and so then in that case, you could do the shortcut, which is just multiply the magnitude by the excess value.
And just plot it from the horizontal.
Yeah, and just make the length according.
Yeah.
And so what we'll end up with for the final answer is going to be 1 plus, this is what I called KO1 earlier. And okay, so what's the absolute value of this? What happened? Parse error? Let me redefine KO2. Okay, absolute KO2. Okay, and angle of KO2. So we end up with 2 angle of 36.8 degrees. And that's as shown there. And so now looking back at, so I just wrote down what we had from the MATLAB, that's it. Okay, so now looking at the solution, yeah, 2 with an angle of 36.87 degrees. IA was 1.12 give or take with an angle of negative 26.5 degrees. And then now give me 1 second to take a look. So I'm looking at what you did. Just give me 1 second.
Yeah, I was multiplying by the conjugate, but as I thought we had to do was to get a conjugate, and then I realized that now that you just really have to flip the sign, and that's it.
Yeah, you just take the conjugate. That's not
I thought it was supposed to multiply by the conjugate, so I was getting a negative
Yeah.
angle out when I reduced everything, and then
Sure.
I was getting C for B and B for C, because that angle was a negative angle.
Got it. Okay, well, good. It was a good example for everyone to check out. All right, so now moving on to not my email. So moving on to new stuff here. So next time we're going to do the quiz. It will be focused on chapter 9. So could see something very similar to what we just did on the screen here. I'll probably make it a little bit more difficult than this. There's some ways that I can ask you some questions also about overexcitation, underexcitation, generating mode versus motor mode, all that type of stuff. So in addition to just being able to solve that relatively, simple equivalent model for the circuit, I would also recommend, becoming familiar with a lot of that more theoretical knowledge that we got from the beginning of the chapter. All right, let's see where we left off then. Okay. So we were here, and we're sort of at one of those points, which was similar to where we were in the beginning of chapter 9, where we're going through a whole bunch of mathematics, and we're making some assumptions, and we're sort of laying down a lot of the, the theory and the derivation for what's going to be the payoff at the end in terms of being able to analyze different aspects of this very simple system, which is a motor, a synchronous machine with a short transmission line connected to an infinite bus. And so what we were doing last time was essentially just analyzing this system, applying some KVL, some Ohm's law, and what we saw was that for this case, there's going to be this relationship where for higher levels of PR, okay, so if there's more power being received at the secondary end of the line, the receiving end must supply the sending end with more reactive power, and that's because we're assuming that the voltage magnitudes at both ends are going to remain at 1.0. And we've seen before that there's a relationship between real power and voltage angle, and there's a relationship between reactive power and voltage magnitude. So this makes sense intuitively a little bit, that in order to boost the voltage at the receiving end, that receiving end load is going to have to supply some reactive power in order to do that. And yeah, so we left off with this question of what's happening to the what's happening with respect to QS and QR. So it's a little bit of an awkward starting point, but we'll have to just sort of jump in there. All right, so we have the system from the textbook, chapter 10. And we have observed a number of relationships for P, R, Q, R, E, T, C, etc. We've noticed, right, that as PR goes up, so shall QR injected, meaning that it's flowing backward into the system. And we also have seen that QS will be equal to negative QR. So those are the two main relationships that we came away with. So that reactive power must be going somewhere in order to maintain conservation of power, conservation of energy. And where is that power going to go? Into the reactive element of the line. So equation 10.9 tells us that Q line is equal to and that's nothing that's that new, right? We if you were asked this just from circuits, well, maybe the end of circuits after we did AC circuits, What's the real power being absorbed by a resistance or being dissipated by a resistance along the line? I squared R. What's the reactive power being stored by a reactive element? I squared XL. And so, so we can use this value to apply conservation of power to our previous expression. And what we end up with is 1010, which says, okay, QS is going to be equal to QR plus Q line. And if we rearrange this, we end up with Q line. We can actually calculate the value for Q line, and that'll be equal to QS minus QR. We know that QR is equal to negative QS, right? That comes from all the way up here. And so then we can say it's equal to 2 times QS. And so now we observe that the generator the generator must put out 1/2 a reactive power injection that's equal to 1/2 whatever is being consumed by the line. Okay, so now section 4.6, we're slowly getting to the payoff, which is how we're going to apply this to looking at stability. And I replaced the word stability with proper operation right here because when the generator, let's say it goes from supplying 0.5 and drops to 0.49, that's not when stability is lost, okay? As you move further and further away from that value, that's when you get closer and closer to losing stability. So proper operation is supplying half of that value, and once we get below that, then we start getting into the danger zone for losing stability. And the next section, now what we're going to do is talk about exactly how close to the danger zone or how much of a chance we run of losing stability, depending on a number of factors. Okay, so I know this is a different chapter. Section 4.6 was one piece of chapter 4 that we have to go back to in order to understand chapter 9. It actually is not that disjoint. So if I didn't say 4.6, I don't know if you would have even realized it was from a different chapter. But so we're going to quickly backtrack into this one section, and then we're going to come back to chapter 10 and complete the analysis that we were doing. Chapter 4 is more on transmission line modeling, which, for better or for worse, we haven't been paying that much. We haven't been spending that much time on. Right, that's essentially the way we have to do it. So section 4.6 talks about something called surge impedance and surge impedance loading. And I know those terms are unfamiliar, but we will explain them. And you'll see how they play into the Chapter 10 stuff in a second. Okay, so let's consider, so a little bit of a sidetrack. So let's consider a lossless transmission line with the load ZC, and we're going to call this the characteristic impedance for that line. And we're going to assume, just like, and you'll see this is some of the assumptions from this section are very close to the assumptions from Chapter 10. We're going to assume the receiving end to be the reference. Just like we did in Chapter 10. VR is going to be 1.0 with an angle of 0 degrees, and our current is going to be described by the voltage divided by the characteristic current for the line. So we, right off the bat, know what the receiving end voltage is, and we know what the current flowing along the line is. Okay. So now, so figure 10 is going to present a way of looking at a transmission line model, looking at a transmission line that we haven't talked about too much. So here's my 2-minute explanation of transmission line modeling, which really will be good enough for the purposes of this class. So we really, when we talk about transmission lines, we can split it up into 4 different cases. Okay? So what I'm going to do is I'm going to draw, I need a little bit more space for one, so I'm going to draw a line like this. Okay, we have what are called our lumped models. Which consider VS and VR only. So the lump models are the ones that have 2 endpoints, okay? Now the other side is a distributed model. So in a distributed model, you don't just have VS and VR. You can essentially see the voltage at every point along the line. Right? For the lump models, there's ways of interpolating it and extrapolating what is the voltage 1/3 of the way into the line. But the model itself doesn't specifically talk about that, right? There's an in, there's an out. You can tell what the voltage is on either side. You can't tell really that much about what is the internal voltage. So for lump models, we break those up into 3 different types. We have the short, we have the medium, and we have the long. And so for the short consider the line impedance only. For the medium, we'll consider the resistance and the reactance. And then for the long, we'll consider the resistance, we'll consider the reactance, and we'll also consider the shunt capacitance to ground. So you've heard me talk about the pi line model. This is the pi line model right here. It's used to, it's the more complicated or more accurate, more descriptive version of the lumped type. Okay, so now what about a distributed line model? So a distributed line model is essentially where we take a whole bunch of these models, okay, so in a distributed line model, you can think of it as a whole bunch of these lump line models put together, okay? And we start off with a line that's 100 miles. Then we'll say, okay, we'll represent each mile as its own individual model. So now we can get the voltage at mile 1, at mile 2, at mile 3. And then we say, okay, now we're going to use even more, and every 10th of a mile, every 100th of a mile. So a truly distributed line model would be one where there's an infinite number of segments. And so that would obviously require a differential equation in order to analyze what's going on, because you're no longer, you know, right, the delta x has dropped to 0. So, so now, this section talks, this section 4.6, talks about our distributed line model. And so they give us figure so the distributed line model that they give us looks like this. Bless you. One, two, three. Okay.
Is there a particular reason we're using polarized caps? Just like the curve? Or
Say it again.
is there a particular reason why we're using like the polarized cap? Like
I think that's just the way I'm drawing it. It's not really a distinction. We're not really going into... I think that's just habit from the way I always drew them. Okay, so we have J omega L. All the segments we're assuming are uniform. J omega L. 1 over J omega C. 1 over J omega C. And then we have our characteristic impedance. This is what we'll call block number 1. This is what we'll call block number 2. You can see where this is going. And right, this is our load. And we could obviously use more blocks if we want it to be more accurate, right? So we're only going to use two and a half blocks if you count the one that is associated with the load. Okay. So so we know that no. So I'm going to give you expressions that will describe how this distributed line acts. This is one of the things that if we did have time to go into chapter 4 and do it more in depth, we'd derive this, but we're not. So 436, we're simply going to apply them. 436 tells us that Vx, and where x is just at a certain point along the line, right? So Vx could be 1, could be 2, could be 3, etc., will be equal to the receiving end voltage magnitude times cosine of beta x, we'll explain what beta is in a second, plus sine j sine of beta x, which is equal to 437 allows us to calculate the current and tells us that Ix, and we're close to the end here, Ix is equal to the magnitude of IR, which if you remember up top, right, we know what those are. We know what VR and IR are at the receiving end of the line. Is equal to that cosine of beta x plus j sine of beta x equals IR e to the j beta x, and beta is equal to omega times the square root of LC from the figure above. So you can see that right, it's derived from the reactive elements in there. Okay, so we're going to have to stop right there. We'll pick up next time with this distributed transmission line. We obviously have the quiz as well. The homework problem that we went over today is a really good one to take a look at. Prepare. Yeah.